sort of not really drawn to scale because this is the myofilament level here, where you have the heavy bands and they have the light bands. And we're going to explain the sarcomere on Wednesday. We're going to look and see where the defining borders are of the sarcomeres, and they go into what's called the Z discs and the A bands and the I bands, and how we identify and how we look at these banding patterns between the individual muscle cells. These are, of course, the mitochondria. These are the sarcoplasmic reticulum. Here, these are the T tubules that run vertically, and the T tubules facilitate the process of the calcium that goes into the system. Yes, Carlos?
The what you call it, the actin sites.
Actin binding sites?
Yeah, so they're only in the middle, right?
Right. Well, they would be in here.
Oh.
Okay, where you have the actin and the myosin overlapping.
Oh,
you see the thin filaments here, and the thick filaments here. The thick filaments would be the myosin. The thin
but the
filaments,
calcium is not released from there. It's released.
Right. It's released from the sarcoplasmic reticulum. Okay, and this then shows also another model we have here, which is really good. This shows what I put on the board. This shows you the muscle, the overall muscle, right, with the individual fascicles. And within the fascicles you have the fibers, and then you turn it around and you have the fibrils and the filaments. So these are your sarcomeres, your individual lines. These are your light and dark bands. This is your neuromuscular junction right here. And this is a neuron, obviously, right? It's laying on the last neuron is laying on the first muscle cell, and here's your end bulbs. Here's your synaptic cleft, right? This is your sarcolemma here, and this is your neurotransmitter in the cleft, and the process by which then the acetylcholine receptors on the muscle cell membrane will then bind to the acetylcholine will bind to the acetylcholine receptors, and then kick off the conformational change of the troponin-tropomyosin complex because of the incremental calcium in the system that changes that shape of that blocking protein that then will lift off those actin binding sites. A couple things on the overall macroanatomy I want to talk about is some of the membranes around the muscle. The outer membrane is the epimysium. The inner membrane around the fascicles is the perimysium. And the innermost membrane around the individual fibers is the endomysium.
Isn't that like the neuron in a way?
Yeah.
What's that?
It was similar, like the neuron was.
Yeah, remember I said that the perineurium, right? The epineurium and the endoneurium were all around the nerve. So this is nothing more than peri, epi, and endo, but mysium is muscle. Okay, neurium was of the nerve itself. Okay? So the epineurium, the epimysium, the perimysium, and the endomysium are the membranes around the first three levels of organization. So level number one is the muscle, the whole muscle itself, surrounded by the membrane, the perimysium. The individual concentric circles within the muscle form the fascicles. That's the second level of organization. Within the fascicles we have fibers. Within the fibers we have the myofibrils, which really are a combination of both the actin and the myosin. And then within that myofibrils we have the individual myofilaments, actin being one filament and myosin being the other. Yes. They facilitate the depolarization way with the calcium. So in other words, when the calcium is released by the sarcoplasmic reticulum, it gets picked up in the T tubules, and it can be really distributed very quickly to all areas so that it needs to change the conformational shape of that troponin-tropomyosin complex. So it's a distribution network, really. A very efficient distribution network of calcium from the sarcoplasmic reticulum. When it runs out of the sarcoplasmic reticulum, runs into the T tubules and just gives it a whole other ability to get to those actin binding sites and get that troponin-tropomyosin off the actin binding sites by binding to the troponin and changing its shape. Once the shape is changed, it can no longer fit into those really those morphological or those structural binding sites. They're all very, very shape related in terms of those binding sites. Just as receptors are on cell membranes, right? Acetylcholine receptors are very much structural piece of the puzzle. Needs to fit in there to bind and cause that reaction to occur. Okay. What's that?
I was just going to ask you, when you're finishing, can you go over that? Because I didn't see right
This
there.
model?
Yes.
This model is basically what I drew on the board here.
Okay.
This is the cross section, right? This is the cross section. You can see the epimysium, right, around the outside. You can see the individual fascicles, right? These are the concentric circles. That would be the second circle, and then within the fascicles are the fibers. And then you've got to sort of flip it around this way, and you look at the individual fibers, and you can see the myofibrils and the myofilaments, third and fourth levels of organization. This gives you your neuromuscular junction, where the neuron here is attacking or coming into close contact with the local cell and spilling out the neurotransmitter into the cleft, where it's going to facilitate that whole process of contraction. Okay. Okay, so that's, this is a very complex physiological process.